Welcome back, everyone. Now that we know how to compute antiderivatives much more efficiently, we can now return to definite integrals armed with these new tools. Because the hardest part of evaluating any definite integral is always finding that antiderivative. Just to remind you of the process of finding a definite integral, you first find the antiderivative, then you plug in the upper bound, and then you subtract, plug in the lower bound into that antiderivative. As an example, let's say I wanted to evaluate the definite integral from 0 to 3 of x cubed minus 6x dx. This is certainly not a definite integral that we could compute with geometry, but now that we have our antiderivative techniques, we know that we can use the power rule in each of these terms. For example, the x cubed term is a power function, and to find its antiderivative, we're going to add 1 to the exponent, and then divide by that exponent. It's going to give us x to the fourth divided by 4. And then the minus 6x term, we can't ignore the 6 because it's a constant multiplied by a function. And we're going to take the antiderivative of x, and once again we're going to use the power rule. We're going to add 1 to the power to get x squared, and then divide by that power, which is 2. And so this right here is my antiderivative. It's x to the fourth divided by 4 minus 6 times x squared over 2. And you've probably gotten used to adding a c to all of your antiderivatives, but with definite integrals you don't need to add that c. And that's because when you plug in the upper bound to the antiderivative and then subtracting, plug in the lower bound into this antiderivative, the c will cancel itself out. And so it wouldn't be wrong to include it, but it's also just not necessary. And just to finish this definite integral off, we need to plug in the upper bound, which is 3, and subtract plugging in the lower bound, which is 0. You don't need to simplify this, you can, but you don't need to. This is a perfectly valid answer. And now beyond just evaluating particular definite integrals, I want to talk about some general properties of definite integrals that you should keep in mind. The first is that if I have the definite integral from a to c of a function f of x, and I add the definite integral from c to b of that same function, that is equal to the definite integral from a to b of f of x dx. And the reason for this is that that first integral represents the area under the curve of f of x from a to c, and the next integral represents the area under the curve from c to b. And so if I add those two areas together, that gets me all of the area under the curve of f of x from a to b, which is that last definite integral on the right side of that equality. And using this in an example, let's say that I know the definite integral from 0 to 10 of some function f of x times dx is equal to 17. That's just a given. And say that I also know that the definite integral from 0 to 8 of that same function is equal to 12. Can I use that information without actually knowing what the function is to compute the definite integral from 8 to 10 of that same function? And the answer to that is yes, using the above property. Because I know that the definite integral from 0 to 8 plus the definite integral from 8 to 10 is equal to the definite integral from 0 to 10. As long as it's the same function inside all those integrals, this property will always hold. And from there, we were given that the definite integral from 0 to 8 of f of x is equal to 12, and we're also given that the definite integral from 0 to 10 was equal to 17. And so I can just substitute both of those numbers in, and then I'm just left with the integral that I am trying to find. And from there, it's just an algebra problem, and we're able to find that the definite integral from 8 to 10 of f of x dx is equal to 5. I was able to figure that out without even knowing what the function is at all, just by using the above property. One more property of definite integrals that's kind of a silly one, but I should show it to you anyway, is that the definite integral from a to a of some function f of x times dx is equal to 0. It doesn't have to be specifically a, it's whenever the lower bound and the upper bound are the same number. And the reason for this one is that if the lower and upper bound are the same, that means your area here has a width of 0. There's actually no area here to compute. And so your answer here, as the lower bound and the upper bound are always the same, is going to get you an area of 0. And as an example, let's say I was computing the definite integral from pi to pi of e to the negative x squared dx. It's a very intimidating looking integral, and you would not have a good time trying to find that antiderivative. But if you notice, the lower and upper bound are the same number, that being pi, and so I know this definite integral has to be equal to 0. And the last property for this video is that the definite integral from a to b of f of x dx is equal to the negative of the definite integral from b to a of that same function. And notice that all I did here is I switched the order of the bounds, and that gives me a negative out in front. And the reason for this one goes all the way back to our definition of what a definite integral is. And the definite integral was defined by the limit as n approaches infinity, where n was the number of rectangles that we were adding up, where we first started with an approximation with a certain number of rectangles, and we let that number of rectangles approach infinity. And that would give us the exact area under the curve, and this right here was how we defined what a definite integral is. If you focus in on that delta x right there, you might recall that delta x was defined to be b minus a divided by n. And so if I were to just switch the order of a and b, I have to put a negative out in front to keep this thing to be equal. And so if I switch the order of a and b on a definite integral, that's why I get a negative value out in front. Now there are many other properties of definite integrals, but these are the main ones that we're going to highlight in this course.